Alrighty. Okay, so assignment number 4, just watch out the deadline, and the makeup lecture, I'll release them shortly after today or maybe tomorrow the latest. You definitely got enough time to catch them up before the final exam. I'll also talk about your exam at the end of today, at least hopefully 5 to 10 minutes. And there's still a chance to do course evaluation, optional if you want to participate. It's up to you. I'll remind you maybe again a little bit later this evening. And office hour, still 3 p.m. today, and I'll reach out to you guys about office hours, maybe during the exam period, and also we can hold maybe at least one review session over Zoom to answer your questions. And I will also make some example questions available for you to maybe take a look. Okay, I'll do that. I'll reach out to you by e-class, right? You can just check your email regularly during the exam period. You should be okay. All right, any questions? All right, last class. Let's now try to see, well, just do the usual thing, right? Recap. So last time, we actually spoke about the last bits of binary search tree, and you definitely have to dive into the detail, especially when we talk about searching. Either successful search, in which case it returns on internal nodes matching the key, or if that's unsuccessful search, in that case, you have to return the external nodes, especially the value that you can actually store for the key in this external node must be in between the predecessor and successor in the in order sequence, right? That's really the most important insight you want to look into this example here. And we actually trace some code in Java. You definitely want to get yourself familiar with the code structure here in Java. And we talk about running time. The most accurate bound for searching will be just big of h, depending on how high the tree is. But there's no guarantee about the height in general unless you do something very particular about it, which we'll see today in the heap data structure. That'll be the last one to cover. Of course, the minimum case will be log n, and the maximum case will be n. That one just corresponds to how we talk about the lower bound and the upper bound for the measure of the binary tree, right? You can definitely refer to it also when you do your review for the exam. And we talk about nonlinear versus linear. So both of them are binary search tree, both of them. But this height over here is log n. This height over here is n. So when you try to see the corresponding search on the in-order traversal sequence, this one here nicely corresponds to the binary search that we did on the sorted array, which is log n. On the other hand, this one here will correspond to some linear search on the sorted array, which is linear, big of n. So I want to watch out for these differences. Okay. And we talk about insertion. Insertion is pretty straightforward. It's just not very little extension to searching. So once you have done a search, when you return either the internal node or external node, you got to do something about it for the insertion, right? You can refer to the detail that I spoke about last time, right? That one is not too complicated. And the running time will just be the same. It's dominated by the search. And we spoke about how you can start with the empty binary search tree, and then you can try to insert a series of entries with the keys and see how you can result in a tree that's very unbalanced. That's also something you can do some exercises on over here. And we talk about this important property called the height balance property. And that one there simply say for any internal nodes, you want to make sure the heights of their children must be different no more than 1. So you actually have to do some absolute value calculation, right? That's something we did very thoroughly last time. You can refer to it and see how that would go, right? So I got exercise over here for you. You can take a look, okay? And that's the final page we spoke about today. So this is where I'm going to continue. So this is the last abstract data type we're going to talk about for this course. It's called priority queue, very practical application. You can see some example use on the slides. For example, if you want to regulate the network traffic, for example, video streaming might be given higher priority than textual messages, on the website, things like that. So everything is somehow associated with the priority. The lower the key value, the higher the priority. And also, entries may have the same priority, right? And also, you want to compare priority here with the FIFO queue that you also learn, which is pretty basic, right? All right, so we're going to continue from here to develop further to see how we can implement the priority queue. We're going to see basically 3 possible implementation for priority queue. We're going to start with maybe linked list, first of all. And for linked list, there are 2 possibilities, which I'll talk about in a moment. And once we finish the discussion about implementing priority queue using list, we're going to see how we can implement it using a heap. That's really the more standard implementation that's very efficient. That's something we'll get into in a moment. Okay. So this is where we are. I'm going to switch back very soon. Let me just tell you where we are. So in slide number 6, so these are simply the standard operations you can perform on the priority queue. You can go over them. It's pretty straightforward. Especially, we're going to focus more when we talk about a heap, how you can do insertion, and also how you can do removal. And also notice that when I say remove min rather than removal, there's a meaning to that, which we'll get into. I just noticed that when you study for that. But for priority queue, when you say remove min, you mean to remove the entry with the minimum key value, which has the highest priority, which makes sense. All right, so let's now talk about how we can implement a priority queue using 2 possible strategies. Both of them are more or less like a linked list. Okay, let's talk about it. Okay, we can fill out some blanks together. It's a nice exercise, also to brush up, for your exam, right? So let me explain this. So we got approach number 1 and also approach number 2. Approach number 1, we are trying to maintain a sorted list for the priority queue. So the key is going to be sorted from the smallest to the largest. So meaning that, so you can think about this one here is always going to be the entry with the lowest key value, smallest key value, or highest priority. So this one will be the minimum key, right? That's something we'll guarantee. And also, if you take, okay, let me just say that will be the highest priority. And if you look at any arbitrary adjacent entries over here in the list, because it's sorted, you can also draw the following property as well, right? If you look at any adjacents, Ki and also Kj. So that means over here, Ki should be less than or equal to Kj. Could be equal because we allow duplicates for the keys, right? Less than or equal to. So that's sorted. So that's the property for the first list. On the other hand, for the second list over here, no assumption. Unsorted, arbitrary. All right. So now, given these 2 fundamental data structures over here, we're going to use them to implement a priority queue. So this table here is going to summarize the standard operation for a priority queue. We're going to go over each one of them. And then for each one of them, we're going to consider for strategy number 1, sorted list, and strategy number 2, unsorted list. What should be the corresponding running time, right? We can go over this table very quickly, but it should be rather straightforward. Okay. Let me start you with something very simple, which I don't need to bother you too much. For size and it's empty, if you just remember what we said before about trading the space for time, so we can most likely just store some attributes for the size. That will be big of 1, right? Trading space for time, right? You can think about big of 1 and big of 1. Just checking to see whether the size is 0, right? Straightforward for both. Now it comes to the more interesting bit. Number 1, minimum. Minimum means we want to extract the entry from the priority queue with the lowest key value, meaning the highest priority. Now, what will be the running time for both strategies? For sorted list, what will be the running time? Do we need a loop, though? Not really, because the head over here guaranteed to be the minimum. That's the convenience of having a sorted list, right? But don't worry, everything comes with a cost. Being efficient in one way might cost you something in the other way. We'll see. Okay. So you can see that big of 1 to just get to the head. And then for unsorted one, you just got no way around. You got to run a loop to search for the minimum, which will be big O of n. Right? It's going to be linear time. And then let's now talk about insert. Let's say I want to expand the queue with a new entry, right? In the case of, let's say, unsorted list over here, would it be expensive to really insert into unsorted list? It's unsorted anyway. Does it really matter what I put it to be? It's not going to be even more unsorted or less unsorted. So why don't I just insert front, which is constant, right? So that's why I can simply say big O of 1. All right? Or if you got tail, you can also insert to the last, up to you, right? I'm just saying, insert it into unsorted list, just efficient. What about sorted list? You want to make sure after insertion, the list remains sorted. Doesn't it sound like something we learned already? Insertion sort? Oh yeah? So that one there is going to cost you up to big O of n, just like insertion sort. All right, so that's about insertion, okay, which we'll see as well. Okay, insertion, and let's talk about removal. So removal means we want to extract the entry and also remove it from the queue, so we don't need to worry about it anymore, right? A little bit like a pop, really, operation for stack, a little bit like that. Now, if I want to remove, it's really the same as like a min, really. If I want to remove the min for the unsorted, for the sorted list, it will be big of 1. I just remove the first one, no loop involved, right? Big O of 1. And if I want to remove the min from the unsorted list, I need to find where the minimum is, which will involve a loop. All right, so that one there is going to be big O of n. All right, it's a kind of like a table you have to know how to draw yourself if you have alternative implementation strategy using data structure. Beyond this course, this is a kind of a summary table you want to know how to make yourself, right? It's going to lead you a long way, right? All right, so let's now make a concluding remark and then we can move on, right? It's a very straightforward definition. There's really not much to really stay any longer. When should you choose approach number 1? That's the follow-up question. Based on the running time, you know that, for example, here, these are the more efficient operation. So that means if these two kind of operation are required or demanded more often, you should really choose strategy number 1. Okay, so I'm going to write it down for you. So you should really choose this one over here. It will be more suitable if you have the following use cases. Okay, it could be that you got more frequent retrieval or removal of top priority entry. And number 2, you want to avoid insert as much as possible because each one of them is going to cost linear time, right? So that should be infrequent. Infrequent, I would say expansion of the priority queue. So if these two kind of satisfy your application use, then you should really choose strategy number 1. Otherwise, symmetrically, you should choose strategy number 2, right? So that's kind of the rationale behind. All right, any question about this? All right, that's good. And we're done with basically the list implementation of priority queue. Let's now get to the final data structure, heap. All right, that's an interesting one. We have learned so much about trees so far, and this is where we're going to synthesize everything together. And we'll see. You also see some concept which we learned earlier, which will be useful for defining a heap. Okay, let's now see how we can define that. All right, so if you look at slide number 7, that's the table I just went over with you. You can double check, and then a heap. By the way, for those of you who actually completed 2031, you may also heard about a term called heap, like as opposed to stack. It's like a memory that's kind of more permanent than stack, right? It has nothing to do with this. Don't get confused. So this heap here is a tree. It's nothing about memory, just in case you're confused. All right? Nothing to do with that heap. You kind of overloaded the term. Okay? All right, so for the heap, it's a binary tree. And it's going to store entry for each node, just like before, like a binary tree. And then this is one example I'll go over with you. Okay? So now you can see each node over here. For example, you can see on the top, I got 4 and C. The 4 here is a key value, and C is a data value. Data value is still not that important, but we're going to focus more on the key, right? For searching, I'll put in quotes, searching purpose, but we'll get there. All right. For heap, in order for a binary tree to be called a heap, you have to satisfy 2 properties. One is to do with a relational property, to do with the keys themselves, which we're going to go over second. Okay? And the first one, the bullet point here about structural property there is more about the shape of the tree. The structural property here guarantees about the running time or the heights of the tree. Okay? So I'm going to talk about structural property first because that's something you learned earlier already, so I don't need to spend too much time. Okay? All right, so just remember, whenever you want to review about a heap, there are 2 properties. One is called a relational property, right? The other one is called a structural property. Okay, let's talk about structural property first. As simple as the binary tree must be a complete binary tree. I'm pretty sure you know what a complete binary tree is, right? Maybe? Make sure you review before the exam. Complete. All right. And for complete binary tree, I'm not going to just go over all the details again, because you can definitely refer back to the binary tree lecture, please. And then, so there are different parts about, okay, so the structure one, slide number 10. So these are the three conditions, all of which have to be satisfied in order for the binary tree to be a complete binary tree, right? That's something consistent with what we learned earlier. Let me just use one example to remind you very quickly about some facts. Okay. So this is about structural property, especially you want to just keep yourself remember whenever we talk about structural, it has to do with the heights of the tree. This is where we can guarantee the heights. Let's say if you want to do some searching, or you want to do some insertion, deletion, the height is guaranteed to be bounded in the best case, log n. Okay, I can tell you right away, the height is going to be bounded to log n. Right, so for that, let's now review very quickly. Okay, so if you recall, let's say the height of the tree is h. And in this case, because it's complete, it's going to be log base 2 n, and take the floor, right? And then if you recall also, we said that this is level h, this is level h minus 1, and this is level h minus 2, right? Just remind you when you review the definition, that's where you should really look at. So you can see h minus 1, and also h minus 2, all right? But you can definitely look at the definition according to the levels. That one I can leave to you. And let's just review the following. What about the maximum and minimum number of nodes for a complete binary tree? There's certain range. It's not full, so there's a range over there. Right? If you recall how we derived the math from previous lecture, we're going to remind you, for all the way until h minus 1, right? This part here is completely full. Okay? So for that part there, we say the number of nodes from levels 0 to h minus 1, right? All the way to h minus 1, starting from 0. It's going to be 2 to the h minus 1, and please review the math about how you can derive this number. You have to review the sum of geometrical sequence, right? Look at that. It's from the previous lecture, okay? And once we have got this part over here sorted, the minimum will be we got only one node at level h. It will be the maximum if we got the whole thing completely full in the level, right? Which would be 2 to the h, right? Let's now write this down, and then we're done with the structural property. So the minimum number of nodes will be 2 to the h minus 1 plus 1. And the maximum number of nodes will be 2 to the h minus 1, the common part, plus 2 to the h. All right? And if you want some simplification, of course, this part here is simply 2 to the h. And this one here is simply 2 to the h plus 1 minus 1. Right? That's something we said earlier. Just remember, in order to be a heap, the necessary condition is it must be a complete binary tree. But it's not sufficient. Being complete doesn't really mean it's a heap. You need to also satisfy the second property for the key value, which is something we're going to spend much more time on. All right? Question so far? All right, let's talk about the second property, which is interesting. The second property here, let me go over a little bit slides with you. So when you study for that, you can also know where to go. It should be slide number 9. Sorry, somehow in the slide, I kind of swap the order, but it doesn't really matter. Doesn't matter which one you study first. Okay, it's called relational property, and it's called a heap order property. All right, so that's sometimes I might say HOP for acronym, right? Heap order property. And let's now go over the heap property by some example. But this is what you want to remember. Every time you look at any node that's internal rather than the root, the key of the node must be larger than or equal to the key of its parents. That's the heap order property. I'm going to see exactly how to understand this. For example, you can see that 5 larger than or equal to 4. 6 larger than or equal to 4, just for example, right? And let's now go over this in different properties. So there are different properties you want to, different lemmas. How about that? You can derive from this property here. Okay. Number 1. Property 1. Any leaf to root path has sorted sequence of keys. Any leaf to root path has a sorted sequence of keys. Okay, I'll give you 2 examples. Let's say sequence number 1, root to leaf to root, ancestor path basically, right? 1, oh, let me make it bigger. If you look at this path over here, if you go leaf to root over here, 12, 9, 5, and 4. Non-ascending order. Decreasing, basically. Okay, that's property 1. And I can give you another example. Let's say here, let's say 13, 7, 6, and 4. That's also sorted. You can look at each of the leaf to root path, guarantee the keys should be sorted. Okay, and then the consequence of this, where is the minimum key? Given this, the minimum key of the whole tree should be the root. That's the most important property of a heap. Okay, we're going to use this property here for heap sort later. Okay, okay. So property number 2. The minimum key exists in the root. And we can make this even more general. If you consider each subtree, the root of that particular subtree also is the minimum key for that particular subtree. All right, so let's say, for example, the biggest subtree is here. That's the biggest one. So you can think about the 4 over here is really the minimum key for the whole tree. The minimum key of the whole tree. On the other hand, if you look at the 5 over here, so 5 is the root of this particular subtree. As far as this subtree is concerned, 5 over here is the minimum key. All right? So that's is a really nice property. Okay? So this is the minimum key of this subtree. Okay? There's another property that's also very important. When you consider, okay, so the heap order property only talks about between child and also parents. What about sibling? It doesn't say anything about it. That means there's no order imposed between sibling keys. Okay? I'm going to write it down first and then I'll illustrate to you. So property number 3. The key values between the left subtree and also the right subtree are not related in any way. Not necessarily. For example, if you look at the 15 over here and also the 9 over here, they're not really related. Okay? Not related in the sense that as long as this 15 is larger than equal to 5 and also 9 is larger than equal to 5, then we are fine. They themselves are not related in any way. Okay? So all these properties are important, especially number 2. So we talk about 2 properties for a heap. The structural property being a complete binary tree, and the relational property here about the relative order of the child keys and also parent key. So that means every time you want to do any update to your heap, you want to make sure both the structural property and also the relational properties are maintained. So this is going to make the insertion and deletion a little bit complicated to really operate, to really restore the property properly. That's something we're going to go over. Okay. Any questions so far about a heap? Very good. Okay. Let's now do one more warm-up example, and then I'll just pause the recording and make sure you have gone through, and then we'll do insertion deletion. Okay. Now, based on what you have learned so far about what a heap is, right? Let's now consider all these candidates over here. I got 6 examples here, simple ones. Are they heaps? Is this a heap? Well, there's no child nodes over here. In some way, there's no way to violate the structural and also relational property, so it's a heap automatically. That's the smallest heap you can have. It is definitely possible. In some way, this will be almost like a base case or last iteration for heap sort. You will see what I mean later. Okay, okay, so this will be the smallest possible one node heap. Okay, and then what about this one here? Is this a heap? First of all, does it satisfy the structural property? Indeed, because up to here is fine, but in the last level here, you're filling out from left to right. So this is the left child, so that's fine. Okay, so let me just annotate it. So this is really the left child. Okay, so this and also 6 larger than or equal to 4. So it is a heap. You got to check both the structural and relational property. And what about this one here? Is it a heap? Does it satisfy structural property? It does, because it's still filling out from left to right at the last level. However, 4 larger than or equal to 6 is false. So it violates relational. Okay? So this is the left. So it satisfies the, oh, how about this? I'll say it's a complete binary tree. But it violates the heap order property. Okay? Because if you try to say 4 larger than or equal to 6, it's definitely false. What about example 4? But now 6 larger than or equal to 4 is actually right. Is it a heap? How come? Structural, right? Because at the last level here, we're filling out from right, not from the left, right? Okay. So this one here, this is the right child. So this is not complete, but satisfies the heap order property. You got to be both. Right? You can see example number 5 and number 6, they're both full binary tree. And full binary tree tells you it's complete automatically, right? So just remember the logical relation. If you got full binary tree, that implies it is complete binary tree, right? It's a very nice little property to remember, okay? So both of them satisfy the structural property as a heap. What about relational? 6 larger than or equal to 4, 8 larger than or equal to 4. Good. 8 larger than or equal to 4, and 6 larger than or equal to 4. And you can see that 6, 8, 8, 6 doesn't really matter. So there's no relationship between the siblings whatsoever. Okay. All right, so both of them satisfy the structural and also relational property. So they are a heap. All right, so just give you a little bit more idea about what a heap is. All right, let's now talk about insertion and deletion, how we can update, how we can expand and shrink the heap. You will see that on slide number, I believe that's, okay, let's see. Slide 11 are the heaps that we just talked about before, and about the operations. Yeah, this slide here just like a summary about the different operations. So the first one here, we don't really talk about it because that one there, how do you extract the minimum key from the heap? Just return the root. That one's easy. So we don't even talk about it, right? Just remember, it's a big of one. But I'm going to talk about number 2, how we can do insertion and how we can do deletion. So in the case of heap, is going to correspond to the heights of the heap. But since it's a complete binary tree, the height is guaranteed to be log n. I'm telling you the conclusion already, but I'm going to see exactly how that's going to work. We'll talk about insertion and deletion. And just get ready to draw. It's actually quite fun to actually operate through, all right? If I make any mistake, please let me know. I did practice earlier this morning. Hopefully I'll be fine. So if you look at slide number 13, so this is more like a algorithm, like a pseudocode to kind of show to you how things will work for insertion, but I'm just going to use it directly on the diagram. Okay, I'm going to show you the different step. We don't really have Java code for that. For those of you who might be interested, you may want to see how you can implement a heap yourself. So you can also implement heap sort at the end. Okay. Okay, let's now take a look. All right, insertion over here. Let's say we want to insert a new entry right here with the key value 2 and also data value t. Okay. First of all, let's now insert the entry in such a way that we're going to maintain the structural property. Where should a new node go? Can it go this way? No, because you got to fill that from left to right, agree? All right? So it must go as the rightmost node visually. So this is currently the rightmost node. If I want to insert a new entry, I should really create a new node as a left child over here and put it there. That's step number 1. All right? In case you already got things already full, what should you do? You should just introduce another one here, right? Depends. All right? So now in this case, for step number 1, we're going to, I'll write it down here. For step number 1, you're going to store the new entry as the rightmost node at level h. Of course, there might be some special case where you're going to introduce h plus 1. It might be possible, but that's an edge case you can deal with when you write the code. So what I do is I'm just going to put it here, and then I'm going to put a new node right here. It's going to be 2 and t. As far as the structural property is concerned, I'm good. It's still a complete binary tree. But is it a heap, though? Not really, right? Especially you can see right away, 2 larger than equal to 20, false. Right? So here comes the sophisticated part for the heap, right? So the idea would be, since we make the updates from the bottom level, so there is a process called up heap bubbling, where you're going to go all the way up to the root and do some swapping. You only swap when necessary. All right, that's where we're going to see. Okay, but just before that, let me give you the turn. First of all, this is the height of the tree. Okay, so it's called up heap bubbling. All right, so we're going to go from level h all the way to the root if necessary. Okay, so think about over here. This is level h, right? And for each potential swap we're going to do, we're going to identify 2 things, C and P. Sorry. I really meant to say rightmost. Did I say leftmost? Huh? Because if I look at this level here, so this is the rightmost. Make sense? Yeah. Of course, this happens to be the left child. But if you look at this particular level over here, this is rightmost. So there's a rightmost for the level. All right. Good question. All right. All righty. All right. So for each step, we're going to identify 2 references, C and P. C for child and P for parents. So for the first one, I'm going to identify this one here, which is the node I just inserted as the C, and this one as the P. And you're going to do some comparison, which will check the relational property, right? So for this one here, you're going to check to see, this will be step number 2. Is the key of the child larger than or equal to the key of the parents. And the key for the child is right now 2. And the key for the parent is right now 20. Apparently, that's wrong. False. That means we're going to do a swap. All right, if you do a swap, it's more like a constant operation to play with the references, right? I'll leave the implementation detail to you. When I say swap, I really meant swap. So 2t becomes over here, and 20b becomes over here. It's a swap. But we're not necessarily done yet, because we have only taken care of as far as this part is concerned. What about here? We're going to see. All right? So for step number 2, we actually compare this. And what about step number 3? For step number 3, we are still going to identify certain nodes. Right? So we're going to do, basically, this is not P anymore. It's now the child. Its parent is P. C and P. Right? Go up one level. It's why it's called up heap bobbling. And then over here, this will be step number 3. We're going to compare is the key of the child larger than or equal to the key of the parents. The key of the child is 2, and the key of the parent is 6. 2 larger than or equal to 6, false. That means another swap. That means we're going to swap these 2. That means 2t becomes over here, 6z over here. We are not necessarily done. We got to check again. Okay, so what we just did was step number 3, and let's do step number 4. And for step number 4, we're just going to do, let's see here. One moment. Okay, let me see the color here. Okay, good. Yeah, so this is not P anymore. It's going to be C, right? So this is a P. And then, so this would be step number 4. Is the key of the child larger than or equal to the key of the parents? The key of the child is 2. The key of the parent is 4. 2 larger than or equal to 4, false. So another swap. Okay, swap this and swap that. So 4c over here and 2t over here. As soon as you get to the root, you cannot do any more swap. So it turns out 2 over here is the new minimum key, which makes sense. All right? So this one tells you whenever you do insertion, you got to start from the bottom there because that's where the insertion goes to, the rightmost node at that level. And then you may have to go all the way up to the root to do the swap. Okay? That's really the outward bobbling. And if you look at the contents over here, we got 20b, 6z, 4c, and also 2t, right? So that's the new contents. And we got these steps over here, right? Yeah, practice this, yeah, when you actually study for that. And let me say a little bit more about running time. So for the up heap bobbling here, you can think about we basically do how many levels should we do maximum? Go ahead, question first.
Do we not also have to check against the other child nodes?
No, you don't need to. So but we don't really do any proof over here. It turns out you only got to do one particular ancestor path. That'll be enough. We don't really prove it. Yeah, turns out. All right. So let's now talk about running time. How many levels do we do? Maximum, the height of the tree, which is guaranteed to be log n because it's complete. So the number of, beg your pardon, number of levels will be big O of log n. And it's because we got a complete binary tree. And for each level, what do we do? Each level, you can see we basically just try to compare this relational property here. And also we do the swap when necessary. And swap is just about changing the references, like a set of references. That should be constant as well. So 2 things. Number 1 will be to compare. And then to really do a swap. And it will be just big O of 1. So overall, it's going to be big O of log n for insertion. Question?
Like before the swapping, like
Yeah.
when you add the actual node,
Yeah.
what's the runtime for that?
The swapping itself is very cheap. It's actually big of one.
Before the swapping, like where we actually add the node as
Oh, add a node should be very straightforward. You can, well, I think that this one is more implementation detail, but that's something you can try. So for example, you may maintain maybe certain reference, like, again, trading space for time. You may say, where is the rightmost node right now at the moment? Once you maintain a reference there, maybe it'll be easier for you to find where to insert. That'd be more implementation detail, but that should be constant time. Shouldn't use a loop for that. You shouldn't need to. Okay. All right, so about insertion. Yes.
So usually, like the most popular way to do this kind of insert is just keeping a reference to the most the one you want to insert at.
Yes. Or to be more precise, if I were to implement this, I might keep a reference to maybe not the rightmost node at the moment before the insertion. Maybe I'll point to the node where this will be the next one to insert a new child. Somehow you want to be a little bit more clever about the implementation. But I'll leave that detail to you. Right? Too bad there's no programming test number 3. Otherwise, we can test you that. Don't worry, there's no. Yeah. Okay, insertion. All right, deletion. Deletion is also very interesting because we talk about up heap bobbling, and deletion turns out to be down heap bobbling. But it's slightly more complicated, slightly. You got to do a little bit more comparison, okay? But we'll go over together. And again, if you go to the slide for the down heap bobbling, it also shows you all the steps. I'll let you read the text, but I'll show you exactly how to do it, okay? And then you can also think about how you can implement it in Java, right? Okay, for deletion, first of all, when we talk about deletion from the heap, it's like when you talk about deletion for a stack, you don't really delete like arbitrary item from the stack. You only delete the top. When you want to delete from the heap, you only delete the minimum key, which is in the root. Okay? So deletion here is really to delete the entry with the minimum key, which we know is at the root. First of all. That means we want to delete this guy over here. But the problem is we cannot just delete it without having something to do with the subtree. I got to do something about it. So now the idea will be take the rightmost node from level H and then delete it and replace it for the root. All right? So rather than adding as a rightmost node, we're now taking the current rightmost node, delete it, and put it at the root. That's the first step. And once we have done that, we have already satisfied the structural property for the heap. But what about relational? That's where the down heap bobbling will come from. All right, let's now do that. Okay. So step number 1, we're going to actually, first of all, store the key value. Usually when you delete, it's like when you pop from the stack, you will actually return the old top. So if you want to delete from the heap, you also return the minimum key right now. Okay. So you can say store the key k from the key of the root, which is 4 right now. Right? So 4 is the current minimum. So I just want to return 4. So we want to return 4 at the end. All right, so and then we're going to say replace the root. Replace the root by the rightmost node at level H. Okay, so these are the two things you got to do combining step number 1. Meaning that I'm going to delete this node here and then use its value to replace this root over here. So 4 is gone. It's stored somewhere before I return. So this one here is going to be 13 and then W. And for your reference here, you can think about this is the root, of course. Okay, that's step number 1. Now, starting from step number 2, I'm going to do somehow down heap bobbling. But now the problem is, when you do up heap bobbling, you have a unique parents. So there's a unique path for you to go to the root. But now if I want to go downwards, should I go this way or should I go that way? Right? That's sounds like the extra comparison I will have to make. According to the algorithm, here's what you got to do. So let's say this one is the parents, and where should be the child? You look at the child key values over here, 5 and 6, and choose the minimum one, or choose a smaller one. Again, we don't really prove about this. You can think about why we'll choose a smaller one. You can think about it, but that's not required for executing the algorithm. So I'm going to make some annotation for you. So this one here is the child with the smaller key value. Okay, I'm going to choose that one. And that one there, I'm going to name that as C. So this is an extra step you got to do, which doesn't exist for the insertion, like a up heap obbling. And then I'm going to compare the relational property. I'm basically going to compare whether or not, so this will be step number 2, is the key of the child larger than or equal to the key of the parents. 5 versus 13. Okay? So 5 larger than or equal to 13, apparently that's false. What should I do? Swap. Okay? So what I do is I'm going to swap this one and with this one here. So 5A and also 13W. One thing for you to think about is if I didn't choose this child node over here, if I chose this guy here and put it here, let's say 6 and Z, it's not good. Because 5 here is still smaller than that. I'm still violating the property. That's one like an informal way for you to convince yourself. Right? That's an aside. All right, so now we are done with the first one here. So that'll be step number 2, right? So for step number 2, we did this, and we did something very similar, okay? And for next step, so this is not C anymore. It's going to be the parents. Now we got choices. Should I go to left or right? Right? Compare 15 and 9. Choose a smaller one, right? So this will be the child with smaller key. Okay, choose that one. I'm going to annotate it as C. And so for step number 3, is the key of the child larger than or equal to the key of the parents? The key of the child is 9. The key of the parents is 13. And 9 larger than or equal to 13, false. Swap. Okay, I'm going to do swap again. So I'll basically swap this and with this. So 13W is here and 9F is over here. Okay, so that was step number 3. And I might have to do another swap. May have to. Let's see. I'm here, and this one here, let's say it's not C anymore. So this one here should be the P, right? I should really choose 14 or 12. 12, right? The smaller one. So this is the child with smaller key. Okay, and then I'm just going to compare, let's say step number 4. The key of the child larger than or equal to the key of the parents. For the child is 12. And for the parents, it's actually 13, right? 12 larger than or equal to 13, false, right? False. So I'm going to do one more swap. So I'm going to swap this and with this. So 12H should be here, and also 13W should be over here. So it turns out, so this is step number 4. The contents of the heap will be, we start with 5A, 9F, and 12H, and 13W. Right? We only need to worry about this particular descendant path that has been chosen carefully. Right? What about runtime? We're basically doing just the opposite direction, right? So the heights, that is called down heap obbling. Right? Again, you got to think about the number of levels will be big O of 1. And now for each level, you're basically doing three things. Number one, you're gonna choose the child. The child with a smaller key, basically, right? And then you gotta compare. And then number three, you're gonna swap if necessary. But all of them are just cheap operation. All of them together will just be 1. Oh, I just noticed that the number of level should be big of log n. I beg your pardon. Big O of log n, because it's a complete binary tree. So the number of level is log n, and each level will be big O of 1. So overall, log n operation. So overall, it's big O of log n for deletion. All right, any question about this? Go ahead.
I know it's not like in the scope of this course.
Yeah.
Is this better done recursively or iteratively?
It's a very good question.
Depends.
You know, it seems to me you can definitely implement this recursively, not a problem. But to me, more intuitively, you might just want to implement iteratively, actually. You would just say go down until you reach the external nodes.
Yeah.
Yeah.
Oh, okay.
Yeah. So this one here, you know, for up heap bubbling, for down heap bubbling, doesn't really matter. Choose the one you feel more intuitive. Yeah. I mean, beyond this course, whether to implement things recursively or iteratively is complete up to your choice, as long as you can justify. Okay. All right, we got one more thing to cover. All right, so for the last thing, and I will wrap up the course, take a short break, and then I'll talk about the exam. All right, so that will be a plan. So just to let you guys know, the other part, first part of the makeup lecture will be to study for removal from binary search tree, which I mentioned briefly on Tuesday. And the second part of the makeup lecture is as follows. So after insertion and deletion, which we just covered, so now the question is, so you can also look at this table here. So both operations are log n. Okay, now the question is, let's say you're given some linear sequence of array. And then you somehow want to construct a heap out of it. So this will be the phase number 1 routine for heap sort, which I'll mention as well. But there are two ways to really construct a heap out of an array. You can either do it top down or bottom up. So these two are the subtopics I want you guys to study in the makeup lecture. Right? So that's actually a sign. But I'm going to assume that there's a placeholder for you to study that, but we can still talk about heap sort very quickly. So that's really something you guys deserve to know before the last class. All right, so that's about top down and bottom up. And then let's now talk about heap sort. The heap sort algorithm. What's the problem here? Same as before, like a selection sort, merge sort, quick sort. You're given an array of numbers. And then, of course, you want to return something that is sorted, right? So the same as before. And now we're going to see exactly how to use a heap to really implement a sort. That's why it's called heap sort. And the idea is incredibly simple. I can just describe it first, and I'll show it to you on the paper. Given the array, you construct a heap out of it. And where can I find the minimum value for the key? The root. Why don't I just keep deleting the root from the tree until it's empty? So every time I'm getting the key from the root, I'm guaranteed to get a minimum at the moment. So I keep getting the minimum. So the sequence I'm getting it is sorted. That's how I sort. Doesn't this sound like something we learned before? Does it sound like a merge sort, quick sort, insertion sort? What did I not mention? Selection sort. So heap sort in some ways is very like a selection sort. You basically keep selecting the minimum. And the way you select the minimum is after constructing the heap, you just keep deleting the root. That's how you understand it. All right, let's see exactly how it's going to be understood, right? That's the last part of the topic I'm going to talk about in person. I mean the live lecture, right? All right, so what's the idea? And I can tell you right away, for heap sort, the bound is going to be n log n, just like merge sort. And let's say you give it an array as the input. So you're going, let's say we got n entries. That's the size. Step number 1. Construct a heap out of this linear sequence. Construct a heap out of the n entries. And this step here is something you're going to study in the makeup lecture, but I can tell you the outcome right away so you can understand the big picture. So there are 2 ways to really do this construction. You can choose either way. Approach number 1 is going to be something called top-down construction. And that one there has big O of n log n time. Slightly more expensive, but easier to implement. The alternative approach to construct a heap is bottom-up approach. And that one there is linear time. So for the first phase, it's either n log n or big O of n. Doesn't matter which one you choose, because the second phase, where we start extracting the minimum key, is going to be n log n anyway. So asymptotically, doesn't matter if you choose A or B. But B might be a little bit difficult, more difficult to implement. You will see once you study the makeup lecture. All right, so once we have done either A or B, what we will get is we get a heap. Right here, it's a complete binary tree, satisfying the relational property, right? So this is the heap that we get. And we know for sure the current root over here has the minimum. And now we're just exploiting this particular heap property. We're going to keep deleting the root. Every time we delete the root, we're going to get a minimum at the moment. It's as if we are selecting a minimum. Keep selecting until it's empty. So we're going to exploit the heap order property, which is relational, by continuing to delete and extract at the same time the minimum or the root until the tree is empty. So the very first time you actually extract a root, you're going to get the first minimum, absolute minimum. And then, of course, the removal itself is going to do the down heap bobbling, which is log n. And then the second time, you get a small, strictly smaller tree, and then you extract the minimum again, right? And etc. Right? Just keep doing it. So what's the running time for this second phase, really? It could be as simple as you think about there will be about n deletion you got to do. Because you got to go from size n heap all the way down to size 1 heap, right? You got to do n times. And then each time is going to give you log n. If you multiply together, n log n. Each deletion. All right, so big O of n log n is the heap sort algorithm. So now you can see why I kind of said in the very beginning of the course, the heap sort algorithm itself is incredibly simple. But to really get it to work, you have to know what a heap is. You have to know how to construct a heap. Also, you got to know how to delete from the heap, etc. Right? Once you know about the heap operation, the algorithm itself is very simple, right? And one more thing to say, you want to compare the heap sort to selection sort. Why is selection sort actually quadratic as opposed to n log n? It's because every time you want to select the minimum, it takes n time, not really log n time. All right? That's something you want to kind of think to yourself, right? But the way they work is very similar. Okay, so that's the last bit I want to talk about. So we're basically done. And then you're going to make sure you study the top down and also bottom up in the makeup lecture. There's one more small thing, which is also the last bit for the makeup lecture. So that's about how you can implement a tree rather than using link node. You can actually use an array to actually implement a binary tree. So that's something I'll let you study as well. That also has very good practical value if you want to take beyond this course. All right. So these are the things. I will make sure they're available tomorrow, the latest. All right. Good. And why don't we, before we take a break, why don't we wrap up the course, take a break, and then we'll talk shortly about the exam. Okay, we'll have time. We've got plenty of time. Let's now wrap up the lecture. All right, let's just reflect a little bit about what we have learned in this course. I think quite much, right? Even though there are certain topics that we didn't really manage to cover, but I think based on what we have learned, I think that's pretty good, right? Okay, definitely lots of programming, right? In your assignments, in the test, JUnits, we didn't explicitly cover that, but hopefully you have some experience with working with a debugger breakpoint in the assignment, right? Recursion, definitely, we did a lot. Generics as well, right? So these three are very nice little, like a nice takeaway for you. Maybe when you go to maybe a higher level course, like a 3311 for software design, I think this one can also help you for sure. And what about the theory data structure part? Arrays, for sure, one of the fundamental ones. Circular array, don't forget that's part of your makeup lecture as well, right? That's also a very interesting way to organize your array for a queue. And also singly linked list, doubly linked list, and stacks queue, double-ended queues. Trees, a lot. Okay, tree, binary trees, binary search tree, balanced binary search tree, and heaps, right, etc. Right, so these are all the things you want to make sure you review thoroughly before the exam. Priority queues and heaps, right, that we just spoke about today. What about algorithm? Asymptotic analysis, we definitely give you the basics about how you can analyze the runtime, binary search, and also how you can search on a binary search tree, which may or may not be a login. Insertion sort, selection sort, merge sort, quick sort, and heap sort, right? We cover all of them. So these are really the basics for you to learn. I think those are really the most common ones you need to learn. Right, we talk about different order traversal for trees, right? So these are all the ones we cover as well. All right, so yeah, so maybe use this as a checklist when you review for the exam. And then just beyond this course, I think this is really the classic textbook. When you get to 3101, that's usually the required textbook. So definitely, maybe your instructor will tend to make it a very theory-oriented course, but I think algorithm is really meant to be implemented and run on the machine. Otherwise, what's the point of having that working just on your paper? So you can take this book and then do some coding practice. That'll be a very nice way to complement if you're into maybe leak code kind of exercises. That's what I usually recommend, right? It's a long-term investment of your time. Cannot be overnight. All right. And I mentioned about compiler, actually, in the beginning of the course. So this will be a point to really refer to those of you who are interested. You have done so much work about recursion on the tree. So now you got all the technical foundation to implement a compiler by yourself. Okay? So this is a tutorial series I recorded for my 4302 many years ago, right before the COVID. But it turns out the series was used quite a lot in the YouTube community. Actually, quite many people refer to it. It's quite a good one. It really shows you how you can build a compiler from scratch, a small language. I would suggest take that as a starting point to see how you can build a compiler using the Antler 4. It's a very industrial standard of implementing compiler. And think about what you can do to expand it to have your own side projects. I think it would be a nice idea for you to try out. Okay, and for that one, definitely compiler is all about trees. You cannot get away from that. Trees, recursion, and you're going to maybe take 3311 software design, but you also learn quite a lot about so-called composite design pattern and visitor design pattern. So these will combine nicely the trees and also OO, right? So these are all nice stuff to really synthesize what you have learned. All right, final one. Yeah, everything you learned in this course will be assumed in 3101. We didn't really cover a hash table, but if you're really interested, you can feel free to go back to one of my earlier courses. I did talk briefly about hash table basics. You can go there. It's not covering the exam, don't worry, but just for your knowledge. Graphs, you'll be in 3101, not this course. And just in case some of you were asking what courses I will be teaching, I will be teaching, this will be something that I teach for software engineering program. It's 3342. For those of you who might be interested in 1090 kind of stuff and apply that to system developments, so this is a nice course to really apply the knowledge to more concrete usage, right? I'll be teaching that in the fall. And if you want to take, for example, 3101 with me, I will be teaching that the first time from the coming fall and the winter. So you can feel free to join me. There will be some programming part for that as well. Little bit, not as much as this course. All right. All right, that'll be it. Thank you so much for the semester. Thank you. All right. Let me just pause. Okay, okay, about your exam. So I think I will also give you guys maybe some PDF, like for the written test, a little bit later. So since your exam will be April 20th, I think we still got quite a bit of time. So I'm thinking about I can give you guys maybe 1 to 2 review sessions. And I'll reach out to you about the time. You'll be over Zoom. You'll be recorded. You can definitely get access to it after that. And there will be another PDF guide, which should just talk about policy, right? The format for the exam will be, you will be given some question booklet, which will include sketch paper. And you will be given answer booklet as well. And we'll get some extra ones, in the exam center. So you can definitely ask for extra if you need to. All right, and no calculator. For example, you should know what 2 to the power 10 is, things like that, right? It should be quite easy. And also log 16, you should be able to calculate, right? Simple stuff like that, no calculator. I don't imagine I will have any multiple choice, but I would say very limited multiple choice. So don't be too surprised if there's no multiple choice. Little to none. Multiple choice questions. Right, so there will be mainly, could be some definitions, and could be some short answer. And short answer could be some explanation, could be some justification. Okay. It's also possible you may have to write some Java code, but not to the extent like a programming test. Not to the extent, okay? Coding, and also you may be asked to trace. Okay, I'll talk about the material you're going to go over, right? Coding and tracing. And you may be given question to do some proofs. Right, we've done some proofs, in the lecture notes, but you can definitely review them. And also, there might be some proofs that will require some basic knowledge, right? That's kind of prerequisite to this course. Okay. Yeah, I think pretty much you can expect. If I come up with anything, I'll let you know. Also, I can give you more concrete tips, maybe during the review session. As we announced earlier, so there will be a question from Jeff, also from Sunila, and also from myself. And then we're going to look at each other's question bank, and then those questions that will appear on our section, I'll make sure you guys can do them, right? So you don't need to review material from other section. You don't need to, right? Just review the material for this section. You'll be enough, right? All right, so what material should you review? I would really say everything, really. Everything that we have seen so far. You definitely want to go for slides, that's for sure. No textbook, you don't need to read any textbook. And also iPad notes, for sure. I would say these two are the most important stuff. Usually the way I generate question for the exam, I just look through these two and look at what I actually discussed in the class, and then I'll generate question from there. Okay, so these two are the most important ones. And then you may want to look at any extra examples, any extra notes that I made available in the lecture site, or any example code. Right? For example, you can see when we actually discuss about the binary tree, right? We actually got a BST node. Right? Maybe look at the example that we did in the lecture. So I might ask you to program something simple from there, right? The example code. Okay, that's good. All right, any question? Go ahead.
Will there be like a lot of opportunities for like part marks? Say like for things like maybe like primitive operations, you got like if you show your work and like a lot of your kind of like ideas.
Yeah, I see what you mean. So, there's something I forgot to, yeah, so here, short answer, so short answer will prove, right? You can think about proofs over here, could be something about asymptotic upper bound, for example. And also maybe given a piece of code, I want you to calculate the number primitive operation. I think since it's not really multiple choice, there will be some flexibility there in the sense that I think I'll give the model solution to the TA, and then they will understand the solution first, and then they'll look at yours to see how close you are. There might be some partial marks. There might be, yeah. How many? We'll judge, right? Okay. Any other questions? We are good? Yes?
Will any assignment material be on the file?
Oh, assignments, right. Yes, I forgot to mention. Yeah, you better review the assignment as well. I may not ask you to reprogram everything from the assignment. I don't think that's worth your time. But the concept you actually learn from the assignment, you may want to review them as well. Yes, indeed. All right. Anything else? All right, I think that's as far as I can think of. But if I can come up with any more tips or any concrete things to suggest, I'll do that. Yeah, question? Will there be a practice final? Not really a practice final, but I might give you some practice question to try. All right, but I would say your priority should be to go over the materials because I'm pretty sure those practice questions wouldn't repeat themselves in the exam. It's just for example, right? Yeah.
What's the usual kind of like thing that gets a lot of students maybe to not do as good as they wanted to with this type of exam?
Well, it's a good question here. I mean, usually exam, maybe this year will be exceptional. Maybe you guys will do just so well, which I'll be happy. Usually exam, I thought they're pretty straightforward. But when we actually grade the exam, I think sometimes your fellow student from previous year, either they left blank or they simply say, I don't know, or they say something like, I don't know. It's really hard to say year by year. I wouldn't really take previous year to say, oh, it's going to happen again this year. I think you guys are doing fine. So just review the material. I thought I teach a little bit better than the previous year. So hopefully you also learn a little bit better. So just review the material and get ready. Yeah, question?
Do you recommend any online resources besides the slides?
You know, to be very honest with you, I don't think you should really need to do any extra readings on online resources. I think slides and iPad notes are really good starting point. That might keep you already very busy. So of course, if there's any particular concept that really you still cannot understand, maybe watching part of the lecture recording might help. Or you can drop by my office hour. I can try to explain. And if it still doesn't help, of course, you can reach out to other resources. Yeah. Okay. Alrighty. Thank you so much. And then I'll see you guys later. Take care.